Hello everyone. Today we are going to be looking at the Addition of Forces lab. Today's lab was put together by Mohammed, so if you happen to see him, tell him thank you. Okay, what are we going to want to do for this lab? We're going to look at force and vector addition. We've done that before, so that should be good. We're going to look at an example of how to add some vectors together. We're going to look at a free body diagram again. And we're going to look at what forces look like when they are in equilibrium. As we have seen before, vector addition is very, very important, so we're going to be going over it again. My goal is for you guys to be able to do this by the end of this semester. So force and vector addition. Force is a vector quantity, so of course we can add them together and use the tip-to-tail method. So here we have vector A and vector B. So when we add them together, we put the one vector there, we move the other vector to the tip, and then you start where you began with the first vector and you end where the second vector ends. That's your resultant. Okay, now we're going to look at the free body diagram again. I know you guys did this quite a few times this last lab, but you'll be doing this for pretty much as long as you are doing physics, so we're going to do it again. Free body diagram, listing all the forces acting on a body. So you've done this before, we're going to do it again. Here's our block on a ramp. Free body diagram, we're going to have the weight, we're going to have the normal force, and we'll have the friction. All right, so here is a new concept, forces in equilibrium. If forces are in equilibrium, that means there is no net force. That means all the forces that are acting on it add up to zero. It also means that the object is either at rest or is moving at constant velocity. If there are only three forces acting on a body, they should form a closed triangle. In other words, you're going to end where you began. If one of them is scaled, then the others can be determined quite easily. So if the block from the previous example is sliding down at constant velocity, then the following steps are: 1, draw the vectors. And here, it's going to be very, very important that you use a protractor. Every protractor has a straight edge, so you should be able to get away with just using that for most things. Second, draw the second vector to scale from the tip of the first vector. Now the scaled version of the second force helps calculating the magnitude of the others. Yes, right, so there's the second force, that would be the weight. Third, draw the third force from the tip of the second force. So we're not going to do like we've done before, where we start where you began and end where you ended. This time it's going to be start at the end of the second vector and end up where you began all of them. And if you know the first two, the length of the second one will be able to be determined, because that will be, everything will add up to zero, and that will be, whenever you scale it, you have your answer for the third one. Which, surprisingly, that's exactly what we're going to be doing in this lab. Alrighty, and here we have a picture of a force table. It's very similar to the ones we're going to be using in this next week's lab. The force table has the features of it should be flat and level. So if you're having anomalous readings, you may need to make sure that the table is leveled. You'll notice that there is a ring around a post in the center, and that there are some strings coming off of it. This picture shows 4 strings, but we will only be using 3 strings, 2 of which will be on a pulley. The table is marked from 0 to 360 degrees. Let's see here. To start off, one of the pulleys you'll want to put at 0. That will be your number 1 string. The number 2 string will go somewhere between 90 and 180. I believe it tells you to do 130 or 140 degrees in the directions. So do that, and those were where your 2 pulleys will be. And then what you'll do is you'll take your force probe and you will move it around somewhere in the opposite direction of the other strings until the ring in the center is centered on the post. At that point, there is no net forces. You'll record what the angle is and what the force is from the force probe. And at that point, you will have one angle, which will be 0. That means you start off on the x-axis. The second angle, so the second vector, will be measured at 120 degrees or 130, 140 degrees, whatever it is, from the positive x-axis. Now, when you do your last one, you'll be measuring it from, if you were to put another set of axes on the tip of the second vector, you'll see that there's a positive x-axis there, and that you'll measure from the horizontal, you'll measure around to whatever the third angle is. And then from there, you can draw some lines and you get to figure out what the mass of the third thing is. They should all add up to 0. So you will be using graphical vector addition, and all angles are measured from the positive x-axis. So that's very, very important. And let's see, here's some things to think about. Can you add two vectors? Hopefully by now you can do that. We've done that enough times. Next, can you add a third vector along with the previous two vectors that will add up to 0? That is something very, very important that you should be able to do, especially by the end of this lab. When adding 3 vectors to 0, where should the arrow of the third vector end up? I want to make sure that you guys know how to do this, because on the final you will have to add vectors, you will have to find the difference of vectors, and you will have to add vectors up to 0. So there will be a problem like what you're doing with the force table on the final. So make sure you know how to do this and you understand it. And that looks like all. So talk to you guys later. Good luck.